Everyone, welcome back to my channel. From this video onwards, we shall start off learning about one important concept of physical chemistry, that is thermodynamics. Thermodynamics is actually having very great importance in the field of research world, and thermodynamics is a very key concept in understanding so many other concepts that actually comes in the field of science. If you consider any competitive examination, there will be one question from the concept of thermodynamics in current scenario. So thermodynamics is a very important concept. And under thermodynamics, there are so many number of topics. And among those topics, here I have taken one topic which appears to be simple but having great importance, that is heat capacity. Know that in thermodynamics, the main importance is used to given for two parameters, that is system and surrounding. So if you consider the system, that can be anything which is having some definite amount of substance. So each and every material will be having some definite amount of heat energy in it. So because of heat energy, the system will exist in a particular temperature. So at normal conditions only, material will be having certain definite heat energy, and because of heat energy, the system will be existing at a particular temperature. Suppose if you want to raise the temperature of that particular system from lower temperature to higher temperature, obviously we are supposed to provide some definite amount of energy to the system in the form of heat. So how much of quantity of heat is supposed to be supplied to the system? How much of amount of heat energy is required by the system so as to increase its temperature from lower temperature to higher temperature is actually called as heat capacity. So in a single sentence, we can define heat capacity as quantity of heat which is required to raise the temperature of the system from lower temperature to higher temperature. This is the simplest definition we can give for heat capacity. And depending upon the way we are presenting the term heat capacity, we can define the term heat capacity in so many different ways. Say heat capacity for a particular amount of substance, that is called a specific heat capacity. Or else if you have taken the amount of substance in a system in some other unit, then it will be some other unit, say in terms of mole, then it will be called as molar heat capacity. And molar heat capacity can be measured by maintaining either pressure as constant or volume as constant. In that case, we used to get two more other heat capacity terms, that is molar heat capacity at constant volume and molar heat capacity at constant pressure. So here I said a total of four different kinds of heat capacities, and now we shall see about each and every type of heat capacity. Among those, first we shall consider specific heat capacity. The first one is specific heat capacity. The name itself telling you, the heading itself telling you, it is heat capacity of a specific amount. And heat capacities is actually mentioned with the symbol C. Since it is called a specific heat capacity, it will be suffixed with S. So this is the symbolization of specific heat capacity. Okay. As I said, a system will be already having some definite amount of heat energy. And in order to raise the temperature of that system, we are going to provide energy once again. So there will be a change in heat energy of a system so as to cause change in temperature. So we can say if there is a small change in heat energy of a system, and that will be directly proportional to change in temperature, that is dq is directly proportional to dt. But we are not supposed to leave any mathematical expression with proportionality symbol, which has to be removed by adding equals so as to insert a constant. So dq is equals to cs into dt. But here we are telling about specific heat capacity. That means if you consider a specific amount of a substance which is taken in a system, that means if you have taken 1 gram of a substance in a system, and in order to raise the temperature of that particular material, which is taken in 1 gram, what heat is supposed to be provided to the system in order to raise the temperature by exactly 1 degree Celsius, or you can mention in terms of Kelvin scale also. That is actually called as specific heat capacity. That means the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius or by 1 Kelvin, or from lower temperature to higher temperature. That is actually called as specific heat capacity. So here CS is the specific heat capacity. dQ is the quantity of heat energy that is utilized by a system in order to cause the temperature change of quantity dt, and the weight or amount of the substance that we have taken in a system will be taken as W, or else CS is equals to dQ divided by dt into W. This is the simple mathematical expression that we can give for specific heat capacity. And the definition can be given once again: the amount of heat required to raise the temperature of 1 gram of a substance is called as specific heat capacity. The definition of specific heat capacity can be given once again, and it will be the amount of heat energy required to raise the temperature of 1 gram of a substance by either 1 degree Celsius, or you can mention in terms of Kelvin scale, that is 1 Kelvin, will be called as specific heat capacity. So the definition can be written as quantity of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius or 1 Kelvin. That will be called as specific heat capacity. And now we shall go for the second type of heat capacity, that is molar heat capacity. In case of molar heat capacity, the amount of substance will be taken in terms of some definite amount of moles. Say if m moles of a substance is taken, and in order to raise temperature of this particular substance by a factor of dt, we are supposed to provide the heat energy, and the quantity of heat energy that will be supplied will be equals to dq. And for m moles of a substance, the change in temperature will be directly proportional to quantity of heat supplied. So once again, we will remove the proportionality symbol by adding a constant. So dq is equals to cm into m into dt, wherein dq is the small quantity of heat provided to the system, cm is the molar heat capacity, m is number of moles of the substance, and dt is the change in temperature, or cm is equals to dq by m into dt. This is the simplified mathematical expression we can give for molar heat capacity. And we can define the term molar heat capacity in a very simplified fashion. That is, it is the amount of heat or quantity of heat required to raise the temperature of 1 mole of a substance by either 1 degree Celsius or by 1 Kelvin. That is called as molar heat capacity. So the definition can be written as quantity of heat required to raise the temperature of 1 mole of a substance by either 1 degree Celsius, or you can express in terms of Kelvin, that is 1 Kelvin. That is the simplest definition you can give for molar heat capacity. And molar heat capacity can be measured either by maintaining constant pressure or by maintaining constant volume. And now we shall see about those two heat capacity parameters. So now let us go with the third term, that is molar heat capacity at constant volume. So we know that from first law of thermodynamics, that is first law of thermodynamics. See, the first law of thermodynamics plays very important role in deriving majority of the mathematical expressions in thermodynamics. So according to first law of thermodynamics, the change in internal energy, that is dE, is equals to the quantity of heat supplied to the system plus quantity of work is done on the system. Since we are discussing about the concept of heat capacity, so we are providing heat to the system, so work is done on the system, so W will be taken with positive sign. So now D is equals to dq plus W, but we know that the quantity of work is done, that's equals to P into dV. So this is the value for W. So pressure into change in volume. So by introducing this term in this above equation, the equation will become dE is equals to dQ plus P into dV. But since we are deriving this expression by keeping the volume as constant, so this whole term will turns to 0. So the remaining thing will be dE is equals to dq. So this much is left. But from the concept of heat capacity, we know that dq is equals to C into dt. This is for molar heat capacity provided 1 mole of a substance has been taken. So dq is equals to C into dt. Since we are maintaining constant volume, so let me take this heat capacity as CV. So at the place of dq, here we can take CV into dt. So dE is equals to CV into dt. Or finally, CV is equals to dE by dt. Since we are maintaining constant volume, so this is the simplified mathematical form that we can give for CV, wherein we can say that it is the ratio of small change in internal energy to the small change in temperature that occurs in a system at a given constant volume is molar heat capacity at constant volume. So you have to remember this particular mathematical expression, and based on this you used to get at least one question in your any competitive examination like your IIT JAM, CSIR NET examination, like so on. So that's about molar heat capacity at constant volume. And now we shall go with one more molar heat capacity provided by maintaining constant pressure. Next is molar heat capacity at constant pressure. So in order to get the mathematical expression for molar heat capacity at constant pressure, once again we will take the help of first law of thermodynamics. So from first law of thermodynamics, so as I told, first law of thermodynamics is the major basis for deriving majority of the mathematical expression in the field of thermodynamics. So according to first law of thermodynamics, the change in internal energy, that is dE, is equals to dQ plus W. But here we are maintaining the constant pressure, so there will be a expansion of the gaseous material. That means if you consider increase in the volume, so when volume is changing, obviously we used to say work is done by the system on the surroundings. So that the term W, that is work done, will be taken as work done by the system, and the convention W will be taken as minus P into dV. The negative sign indicates work is done by the system. Okay, and then in order to get the mathematical expression for molar heat capacity at constant pressure, we shall take the help of enthalpy equation. So enthalpy equation is one more simplest mathematical form that plays a very important role in deriving many mathematical form. So according to enthalpy equation, H is equals to E plus PV. H is equals to E plus PV. So this is called as enthalpy equation, where H is enthalpy, E is internal energy, and P is the pressure, and V is volume. So subject this particular expression for the process of differentiation. So if you go with the partial differentiation, the equation will turns dH is equals to dE plus, so here we have two terms, so we have to apply the product rule. So by keeping the first term P as constant, differentiating the second term dV, and again the same V into dP. So this is the equation. But provided here we are maintaining constant pressure, so this whole term will turns to 0. So the equation left is dH is equals to dE plus P into dV. So here we have the value of dE, that is change in internal energy, that is dQ plus W. But we have the value of W as minus PdV. So by introducing the value of W in this equation and the value of dE in this equation, the whole and sole equation will turns to dH is equals to dQ at the place of W minus PdV, and here we already have plus PdV. So both the terms will get cancels. So the remaining term will be dH is equals to dQ. But we know that according to the molar heat capacity equation, dQ is equals to C into dt. But here the molar heat capacity is measured at constant pressure, so C will be taken as Cp. So dQ is equals to Cp into dt. So dH is equals to Cp into dt, or Cp is equals to d H by dt. But pressure is kept constant, and this is the simplest mathematical expression that we can give for molar heat capacity at constant pressure, and which can be defined as it is the small change in enthalpy of a system with respect to small rise in temperature, that is dt, by maintaining constant pressure. So this is the mathematical form for heat capacity at constant pressure. So totally we have given two terms, that is Cp and Cv, and these two terms Cp and Cv are completely related to each other, and now we shall see what is the actual relationship between the two molar heat capacity terms, that is Cp and Cv. So in order to get a relationship between Cp and Cv, we have to take the help of enthalpy equation once again. So from enthalpy equation, that what we already given in the previous topic, that is molar heat capacity at constant pressure. So from enthalpy equation, so that what we are having, so H is equals to E plus PV. This is called enthalpy equation. But if you consider an ideal gas, so for an ideal gas which is taken in exactly 1 mole quantity, so for 1 mole of gas, in a strictly speaking way, for 1 mole of ideal gas, so for 1 mole of ideal gas we can write PV is equals to RT, provided N is equals to 1. So in this enthalpy equation, at the place of PV we can go with RT. So equation will change to H is equals to E plus RT. So now we shall start off differentiating this equation. In a strictly speaking way, we shall go with the partial differentiation. So on partial differentiation, with respect to temperature, so I can directly say as on differentiation with respect to temperature. So the thing will happen, dH with respect to temperature Tt, that's equals to dE by dt, plus, since R is a constant which will not be differentiated, and T on differentiation will get dt by dt. Both the terms will get cancelled. But we know that dH by dt at constant pressure is equals to Cp, and dE by dt at constant volume is be taken as Cv. So by introducing these two terms in this equation, at the place of dH by dt, I can take it as Cp, that's equals to, at the place of dE by dt, I can take it as dCv plus R, or else Cv on taking to the left hand side, Cv, that's equals to R. So this is the simplified mathematical expression that we can give to say the relationship between Cp and Cv, the two molar heat capacity terms. That means when the work is done by 1 mole of an ideal gas in expansion at constant pressure when heated through 1 degree Celsius is equal to R, which is the universal gas constant. That means the difference between molar heat capacity of a gas at constant pressure and at constant volume is equal to a gas constant. And the value of Cp is always greater than Cv. The molar heat capacity at constant pressure will be always greater than that of molar heat capacity at constant volume. So for this, the explanation can be easily given and it can be easily understood. If you consider a gaseous material and when you are heating that gaseous material at constant volume, no external work will be done by the gas. That means when there is no change in volume, then there will be no exchange of heat between system and surrounding that causes change in volume. That what we used to say, work is amount of energy exchanged between system and surrounding that causes change in volume. But when you kept volume as constant, then there will be no work is done by the system or on the system. In other words, whatever the heat we supply to the gaseous material, that will be used to increase the value of internal energy only. That means if you rise or if you provide the temperature, that means if the temperature of 1 mole of a gaseous material is raised by 1 degree Celsius, that is from the temperature of T degrees Celsius to T plus 1 degree Celsius. When you increase the temperature of a gas by this extent, the increase in its internal energy itself will give the molar heat capacity at constant volume. The other than rise in internal energy, there will be no change in energy, so that the value of Cv is corresponding to change in internal energy only. However, if you heat a gaseous material by keeping the pressure constant, then there will be increase in its volume. Okay, and that is the gas will expand and will do some external work. Therefore, some extra heat energy is required to increase the internal energy of its molecules. So, we are supposed to provide some extra heat energy in order to increase the temperature, because whatever the heat we supply, that will be utilized to perform the work. So to raise the temperature, we need to give some more amount of heat energy to the substance to increase the temperature by a factor of T plus 1 degree Celsius. So in case of Cv, the rise in or the heat energy we provided will increase only internal energy, and that corresponds to molar heat capacity. In case of Cp, whatever the energy we provide, that will be utilized to perform the work by the system initially. Then in order to raise the temperature, it requires some more amount of energy, and thus the magnitude of Cp will increases due to excess supply of heat energy, and thus the value of Cp will be always greater than Cv, and the difference between the two evidently will gives the work done by 1 mole of the gas in expansion when heated through 1 degree Celsius at constant pressure. Thus, the value Cp minus Cv will gives the value of work done by 1 mole of gas in expansion when heated through 1 degree Celsius at constant pressure only. The term heat capacity and its types and the relationship between Cp and Cv, and between Cp and Cv, which one is having greater value and the reason for it. And that's the whole for this particular video.
If the video is worthy, please like it, share it, and do comment. And please subscribe my channel and press the bell icon to get the latest notification in my channel. Thank you very much.